Welcome to the Explainer. Today we're tackling a notoriously tricky but absolutely vital statistical concept. It's an incredibly powerful tool for finding the truth in messy, real-world data. We're talking about instrumental variables. If you've ever looked at a data set and thought, wait, is this correlation just a total illusion? Well, you're in exactly the right place. All right, let's ground this with a high-stakes, real-world scenario. Say you're deciding whether or not to go to college for an extra year. You really want to know if you get that extra year of schooling, will it actually cause your income to go up? Sounds simple enough, right? Just look at the data of people's incomes and their years of schooling. But as we're about to see, the real world is rarely that simple. To break this all down, we've got 5 steps. 1. The causality problem. 2. Our villain, endogeneity. 3. The hero, instrumental variables. 4. The rules of valid instruments. And finally, number 5, the 2-stage solution. Kicking things off with part 1, the causality problem. So when we run a standard regression of earnings on schooling, what we desperately want to find is causation. We want the precise magnitude and direction of the effect that schooling actually has on earnings. But what do we get instead? Just the simple magnitude of association. It basically just tells us that two things move together. It definitely doesn't prove that one caused the other. And man, this really highlights a massive limitation of standard OLS regression. Because OLS fundamentally assumes our independent variable, schooling, is completely uncorrelated with any unobserved errors. And when that assumption fails, we're stuck. We literally cannot answer why the income went up.
Which brings us to part 2, the villain, endogeneities.
Now, I know endogeneity sounds like a scary textbook term, but don't let it intimidate you. It basically just means there's a hidden factor pulling the strings behind the scenes. Your explanatory variable is being influenced by unobserved stuff floating around in your system, which causes it to correlate with the error term in your equation. The mathematical fallout from this villain? It's what economists call omitted variable bias. Whenever our variable x is correlated with that unobserved error u, our standard estimates get totally biased. The math just cannot untangle the true effect of x from the hidden effect of u. Let's look at how a microeconomics textbook explains this with our education example. Imagine this invisible confounding factor. This u is inherent ability, right? Intelligence. People with high innate ability might naturally just earn higher incomes. But those exact same high ability people are also way more likely to pursue higher levels of schooling. So this creates a sneaky backdoor path that totally inflates the perceived effect of schooling on earnings. The data makes it look like school's making them rich, but a huge chunk of that is just their raw ability. So, how do we fight this? Enter part 3, the hero, instrumental variables. Think of an instrumental variable, usually denoted as Z, as a water filter for your data. Right now, our data is murky, right? Schooling is all mixed up with unobserved ability. The instrumental variable takes that contaminated data and literally filters out the junk, leaving us with just the pure, uncontaminated variation in schooling. And that is exactly what we need to find the true causal effect on income. And researchers have come up with some incredibly clever instruments over the years to act as these filters. For example, to filter out that ability bias in education, some have used the physical distance someone lived from a 4-year college growing up. Others have actually used a person's month of birth. Or think about smoking and health. You can't just run a simple regression because genetics mess up the data. So what do they use? The price of tobacco as an instrument. It's brilliant. But you can't just pick anything. That's part 4, rules of valid instruments. If we dive into the matrix algebra from the source material, there are 2 really strict rules here. First, Your instrument must be exogenous. That means the covariance of your instrument Z and the error U has to be exactly 0. Second, it must be relevant, meaning it actually has to correlate with your endogenous variable X. Okay, let's translate that math into plain English using our college distance example. First up, relevance. Living near a college actually has to affect whether you go to school. If it doesn't, it's a weak, useless instrument. Second, exogeneity. Distance to college must have absolutely nothing to do with your innate intelligence. And finally, exclusion. Living near a college can't magically deposit cash into your paycheck. It can only affect your income through the actual mechanism of getting you to attend school. And a really crucial point here is understanding the difference between an instrument and a proxy. Like, you couldn't just use an IQ test score as an instrument. Why? Because IQ is a proxy for ability. It is obviously correlated with that unobserved ability hiding in our error term. A valid instrument has to be completely, 100% detached from that error. Which brings us to part 5, the two-stage solution. So, how does all this build into what statisticians call two-stage least squares, or 2SLS? Now, I know the matrix algebra here might look a bit terrifying at first glance with all the overlapping variables and multiple equations, but honestly, we can translate that dense formula into a super intuitive two-step recipe. Stage 1, we run a regression of schooling on our instrument, distance to college. This creates a purified predicted schooling variable. Let's call it S hat. And this S hat is driven entirely by geographic distance, not hidden ability. Then, stage 2, we throw out the dirty original schooling data, and we regress income on our shiny new purified S hat variable. The coefficient we get from that, that's our true causal effect. And this brilliantly shows why the method works so well. Using directed acyclic graphs, or DAGs, championed by computer scientist Judea Pearl, we can visualize this perfectly. Our instrument Z forces a one-way street. Causality flows from distance to schooling to income. It creates a structural barrier, a collider, that completely blocks those unobserved confounders from flowing backward and messing up our data. Instrumental variables are just the ultimate proof that, yeah, correlation isn't causation, but with the right filter, we can totally uncover the causal truth hiding in all that noise. It honestly changes how you look at the world. So I'm going to leave you with this to think about. Look around you. What invisible variables are secretly biasing the statistics you read in the news every single morning? And what clever instrument could you use to finally uncover the truth?